we are going to talk about the oxidation of odd chain fatty acids. You know, we have done the oxidation of the even chain fatty acids when we are describing about the beta oxidation. If you haven't watched that, please go back and watch so that you can know where we are moving from here. Now, oxidation of odd chain fatty acids. We know odd numbers are like 13, 3, 17, 19, you know the odd numbers. So we're going to see how we are going to degrade the fatty acids with odd numbers. Now let's just take an example. Suppose we have a fatty acid with 17 carbon chain. So let us draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? Now, before we get into this, you know, when you have the fatty acid, it must first undergo the processes, the processes, or the preparation processes, such as the activation, when you are adding the CoA by the help of acyl-CoA synthetase. You know those particular processes we did in the beta oxidation. Then you are going to form the acyl-CoA. We are going to involve the carnitine. That's the transportation process. When we added carnitine, then we transported it through the mitochondrial membrane because acyl-CoA cannot penetrate the mitochondrial membrane. Then we got the acyl carnitine into the mitochondria. Then we change the carnitine with we exchange the carnitine with the CoA. So those preparatory processes, I hope you are well conversant with them. So that inside the mitochondrion, we are going to now start with the fatty acyl-CoA. We're just going to say these are acyl-CoA. Initially it was fatty acid, but now we're going to do the activation and the transportation. So we are inside the mitochondrion. Now, when you have such an odd chain fatty acid, what is going to happen? We are going to run the beta oxidation. I'm sure you know the process of beta oxidation. We have the oxidation, the hydration, the second oxidation, and the theolysis. Please, if you don't know them, you can visit my video on the beta oxidation. Right. Now, when you have the acyl-CoA, you're going to run the beta oxidation pathway so that you're going to leave these particular acyl-CoA molecules one after the other after each round of beta oxidation. So that in the first round of beta oxidation, you're going to get three. You know, acyl or acetyl is a two carbon molecule. So this is 1, 2, then 1, 2, you're going to cut, 1, 2, 1, 2, you're going to cut, 1, 2, cut, 1, 2, cut, 1, 2, cut, 1, 2, cut. Now, in the case of odd chain fatty acids, we're going to be left with a 3 carbon molecule at the end, right? So we don't leave everything. So that you're going to have how many rounds of beta oxidation? So this is the first round, the second round, the third round, the fourth round, the fifth round, the sixth round, and the seventh round of beta oxidation. So let's say here we're going to run 7 rounds of beta. 7 rounds of beta oxidation. 7 rounds of beta oxidation. Alright. Then in the 7 rounds, how many acyl-CoA are we going to get? Now, these are acyl-CoA. So these are our first acyl-CoA, the second, third, fourth, fifth, sixth, seventh. So I'm going to get rid of 7 acetyl-CoAs. Alright, then what are we left with? You'll be left with a particular molecule here. Now, what's the name of this molecule? This molecule is called propionyl-CoA. So, yeah, propionyl-CoA. Propionyl-CoA, the structure is here. We have a C. Then now, this is bonded to hydrogen atoms. That is our propionyl-CoA. Now, what is going to happen to this propionyl-CoA? The first thing that's going to happen is that you're going to carboxylate it. You're going to add a carbon onto propional CoA. So we are going to add a carbon in form of bicarbonate ion, so we can just write CO2, but we are going to add a carbon. Now this reaction is going to involve a biotin. So we're going to require biotin, right? So what is the name of the enzyme that's going to catalyze this reaction? This reaction is going to be catalyzed by an enzyme called propional CoA carboxylase. So we have propional CoA carboxylase. It's going to carboxylate or add a carbon. And this reaction is also going to require some ATP. So this is going to require some ATP. Alright, so that we now have a 4-carbon molecule. Now what is the name of this 4-carbon molecule? This 4-carbon molecule is going to be called D-methyl malonyl CoA. This is just orientation. The D-methyl malonyl CoA. So how does the D-methyl malonyl CoA look like? D-methyl malonyl CoA so that is our D-methyl malonyl CoA. Now, what next? Moving down, we are going to convert the D-methyl malonyl CoA into L. The levorotatory, this is the dextrorotatory form. So the L-methyl malonyl CoA. Alright, now this is going to be done by an enzyme. Now this enzyme is going to be called methylmalonyl CoA epimerase. So I'm going to have methylmalonyl CoA epimerase. This enzyme is just going to change the configuration, right? So that you're going to have our L-methylmalonyl CoA. Now, I told you that this process from the propional CoA is going to occur in stages. For example, this first stage is going to be called carboxylation. Then you're going to have isomerization as the second step. So here I'm going to talk about the isomerization. Here is going to be the carboxylation. Alright. Now let us move down. Moving down, we're going to talk about the rearrangement. Alright. Now, moving down, we're going to convert L-methylmalonyl CoA into a new molecule. Yes. Now this new molecule is going to be called succinyl CoA. Alright. This reaction is going to be catalyzed by an enzyme. Now this enzyme is going to be called methyl malonyl CoA mutase. It's going to shuffle those particular atoms within the structure. Now, let me show you how the L-methyl malonyl CoA looks like. Alright, that is the L-methyl malonyl CoA. Now the succinyl CoA looks this way. Here's an this one. these are hydrogen atoms. Alright, now the meta-malonyl-CoA mutase is going to catalyze that particular reaction. Alright, now what is the requirement for this particular reaction? We have the coenzyme B12. Coenzyme B12 is going to catalyze, is going to be needed for the conversion of the L-meta-malonyl-CoA into succinyl-CoA. Now, where are we going to take this succinyl-CoA? Now, see this. Succinyl-CoA, of course, we know it's an intermediate in the TCA. So, the first pathway is going to the TCA, right? Of course, you know the TCA. We are going to generate the NADH2, the NADH, FADH2. This one can be taken to the electron transport chain to yield energy in the form of ATP. So that is the first pathway. The second pathway, we can take this succinyl-CoA and use it to synthesize heme and porphyrins. Now, hemes and porphyrins are components of what? Are components of hemoglobin. So these are used to synthesize hemoglobin. For the transportation of, so that we can transport oxygen. So this transports oxygen. Alright. Then succinyl-CoA can also be taken to gluconeogenesis. You can form the oxaloacetate, can be converted back to malate. Then you can move all over to glucose, to the gluconeogenesis pathway. So this is alright. That's pretty cool. Now guys, that's it for this video. You saw how we oxidize the origin fatty acid. So for example, this case was 17, can be given 18, 13. So the main process is that you're just going to break it, but you're going to be left with a 3-carbon molecule. That's the propionyl-CoA. So these remaining steps are constant. Just to know the number of rounds you're going to have for your fatty acid, then the amount of the acetyl-CoA you're going to obtain from there. So thank you so much guys. If you found this video helpful, please subscribe to my YouTube channel, comment, and leave a comment right there. So thank you so much, and let's meet in our next video.